Welcome back to Multigrid Methods. Last time we finished talking about the strong approximation property. We're in this second of two slide decks for chapter 6. And we talked about the strong approximation property last time, which was our final piece to show that multigrid methods for the finite element case, where we're trying to solve the finite element problem, ALUL E equals FL. So we discretized the PDE, the Poisson problem, by the finite element method. We obtained a linear system of equations, and now we want to solve this via the multigrid method. And if we use the finite element methodology, then all of our multigrid methods converge without any extra work. We've got everything because we have the strong Galerkin condition. We've got the strong approximation property, and if we use Richardson's method for smoothing, then everything converges beautifully. The last piece I want to talk about for the multigrid method applied to the finite element method is this thing called the full approximation or the full multigrid algorithm. So we haven't discussed this algorithm yet. It is a new algorithm based on the old standard multigrid algorithm. And here's how it works. So I'm going to draw a picture first, and then we'll get into all the definitions. The basic idea of the full multigrid algorithm is we're going to start at the lowest level rather than the highest level. So suppose that this is our capital L up here equal to 5. We're actually going to start down at the lowest possible coarse grid level, and we're going to solve the problem there, and we're going to prolongate that solution up to the level 1 grid. And we're going to use that solution that we got from here, prolongate it up to this level 1, and we're going to use that as an initial guess to a multigrid algorithm, our standard multigrid. And then we're going to do 2 cycles of that. Okay? And then we'll get to here. This is going to give us an approximation now at level 1, which we're going to prolongate up to level 2. And we're going to use that as an initial guess to our multigrid algorithm, where we're going to do 2 cycles, 2 V cycles essentially in this case. We're going to apply 1 V cycle, apply a second V cycle, which gets us to here. We're going to take that guess and we're going to push it up to the next finer grid through prolongation, up to level 3 grid, and then we're going to do 2 V cycles there. Okay, which gets us back up to level 3. And then we're going to take that and push that up to level 4 and then continue. We can continue this as much as we want. For example, we can do 2 V cycles now on level 4. We get a new approximation on level 4, and we're going to push that up to level 5. That's what's called the full multigrid algorithm, the full multigrid algorithm. And there's some nice advantages of this over just using the standard multigrid algorithm. Standard multigrid would be just doing something like this. Okay, 1 V cycle, for example. So let's introduce the components of this. You've probably heard it said that multigrid is what's called an optimal order method. This means that in our finite element approximation that we wrote earlier, I guess I erased that, finite element approximation results in an equation like this. This, of course, is our given forcing vector. This is our stiffness vector, and this is the unknown displacement vector. So if we're given this problem, we want to solve it. If we apply Gaussian elimination to solve this problem, then it's going to require order NL cubed operations, where capital NL is the number of unknowns in this vector here, UL. However, you may have heard it said that multigrid only requires order NL operations. And that's what we call optimal because it can't get any fewer than that. It can't be fewer number of operations or say proportional to the number of elements. There can't be less than that because just filling in or copying in the solution requires that many operations, just adding two solutions together. So this is the bare minimum that you could get in terms of the order of the number of operations required. So this might be something, order, of course, means less than a constant times the amount of work is less than a constant times the number of elements, NL. So this could be a constant, could be 100, or it could be 3, or it could be 50. But the important thing is the work that's required to find this approximation is always proportional, at least in the asymptotic sense, to the number of elements in the solution. So it can't get less than that, because as I said, if I take two vectors and add them together of this size, then that's just going to be order NL operations. We can't get less than that. So you may have heard it said that multigrid is an optimal order method in this sense. And so it turns out that it's the full multigrid algorithm that they're talking about whenever they make reference to this. So we're going to prove a theorem which shows that the work to obtain a solution via this new algorithm is bounded by some constant times NL. Or in other words, it's an order NL algorithm. Whereas something like Gaussian elimination would be fairly expensive. It's order NL cubed, where NL, again, is the number of unknowns. You may have heard of other algorithms that could be applied to solve the Poisson problem, like the fast Fourier transform method. The fast Fourier transform method, just for your fast Fourier transform, FFT, and some people may have heard of the fastest Fourier transform in the West, FFTW. That's an algorithm. So this one requires order NL log NL operations in order to get a solution. Well, this is not optimal, because if it requires this many operations, this is still smaller. Now, it's not much smaller, because if NL, and this can be log base 10 or something like that. You can think about it as log base 10. So if NL is 10 to the 5th, then this is only a constant. Okay, it's only 5. And so 5NL, that's not that bad. It does rise rather slowly. We know that the log of x rises slowly with x, but it does rise with x. So this is not optimal order, but it's still fairly cheap. And so if you're interested in learning about the FFTW, you can see a discussion of that in our book. But we're going to stick to proving this fact, that the multigrid algorithm in this flavor is optimal order. So let me make a few definitions that are sensible. So suppose that f is the given known function in the problem that we want to solve. So the problem we want to solve, remind you, is Laplacian of u equals f, let's say in 2D, with u equals 0 on the boundary. So that's the problem that we want to solve, and this is the f that I'm talking about here, this given forcing function. So if I'm given a forcing function and I have this hierarchy of meshes that I have defined for myself, remember the meshes are tau L, and the spaces that are subordinate to that, finite element spaces, are VL. Well, so if I have this hierarchy of meshes created, then I can compute this vector FL. And what I'm going to do is, remember, we had this thing called the basis BL, and the basis BL had these functions in them called hat functions, phi Lj. Okay, so if I take those guys and I integrate against them, actually I call them psi, but here I'm calling them phi. This is a typo, because so this needs to be corrected. These here should be psi's, psi L, i's. All right, so not phi, we didn't use that notation. So if I integrate these against psi L I, for I equals 1 up to NL, this gives me the components of this vector FL. Okay, so this was what we saw in the finite element process. We need this vector to solve the problem at each level. The full multigrid operator is defined as follows. So we're going to say, so S is for us going to be a level number. We also need a number r, which is going to be a positive integer, but s is our level number. The full multigrid operator at level s, okay, is going to give us the output as a vector called u hat s, and it's defined in the following way. If s is equal to 0, then we're simply going to define this via the inverse. Just invert the stiffness matrix. And the reason why we can just use the inverse is because this thing might only be a 2x2 matrix, something very, very small. And so, or a 1x1 matrix, in fact, we just divide by a constant. It's very cheap to invert that level 0 stiffness matrix. So that's what we're going to do if s is equal to 0. What we're going to do more generally is we're going to take for L between 1 and S. So if we're on level L, or let's say level L minus 1, what we do is we take the previous output from that, that full multigrid operation, and we're going to prolongate it up to the next level. So that pushes us up to level L. So we are at level L minus 1, and we're going to go up to level L. We're going to use that as an initial guess for a multigrid operator. So we're going to put that guy in here to start with, and then we're going to run our multigrid operator r times. Okay, so that's where that r parameter comes from. Remember, we said r is some number in the natural number. So it's 1, 2, 3, something like this. We're going to run the multigrid process. This is our standard multigrid operator, not the full multigrid operator that we're defining. This is the multigrid operator that we had before. Remember, it goes down, up. And of course, if p is equal to 1, then that's just a v cycle. And if p is equal to 2, that gives us a w cycle, etc. So however many times we run this, it's going to give us an output ULR. And that's what we're going to call our next approximation at level L. And then we repeat. Okay, so now to get the initial approximation at L plus 1, we prolongate up to L plus 1. We use that as an initial guess. That is, in other words, so L plus 1, we get an initial guess by pushing the level L solution up and then calling a process which looks like this, but at the next level up. Okay, so this is what's called the full multigrid operator. The picture really describes what's going on here better than the definition, I think. So you start at the bottom and you just invert. Then you go up, you push it up using the prolongation. Then R in this case is equal to 2, so we do 2 V cycles. P is equal to 1, so it's a V cycle. Then we take that next guess, push that up to the next level, level 2 in this case. Then we're going to go to 2 V cycles. Then we take that and push it up. Then we do 2 V cycles, push it up, and then we continue and we stop at whatever level is enough for us. That's the full multigrid algorithm. Now we want to prove that this algorithm actually results in some approximation, which is quite good. It gives us an approximation which is quite accurate, and we don't have to take all that many values of r, or r doesn't have to be that big to get a really good approximation. And the reason is because we're starting out with something exact, and here we're starting out on level 1 with something which is nearly exact, and we refine it through our multigrid iteration, which gives us something at this point which is pretty close to being exact. Then we push it up to the next level. Again, it's a really good approximation. Do 2 iterations of multigrid gives us an even better approximation. So we're constantly improving something which is already pretty good to start with. So now what we want to prove is that what we want to show is that the output of this full multigrid algorithm is something which is very, very close to the true solution that we're looking for, or at least the finite element solution that we're looking for. So here's the theorem. So suppose that in general, if we're given an initial approximation for our multigrid operator at any level L, that if we run that approximation, the multigrid approximation, then the difference between that new approximation that we get, remember we'll call this UL3 because it goes through 3 stages: pre-smoothing, quartz grid correction, and then post-smoothing. Right? So that gives you UL1, UL2, UL3. So UL3 is what we get in the end. And we're going to contrast that or measure that against the true solution on that level. And we're going to assume that that is less than some contraction factor, gamma, which is smaller than 1, times the initial error. So this is showing how much we're contracting by using multigrid. Now we know that this multigrid produces contraction factors because we already showed convergence earlier in chapter 5. We know if we have all the pieces and put all the pieces together, we get convergence. So an assumption like this is a reasonable assumption. Again, this is the true solution on level L, and how we express the true solution is as the inverse of the matrix on level L times the input vector on level L. So there, that guy has to match. All right, now let's make some assumptions. Assume that f is an L2 function. That is in the creation of our initial forcing vector f. Of course, making these corrections. This is wrong. This is not phi L, but it's supposed to be psi L. So that f should be an L2 function, and the R in the full multigrid algorithm, so the R is the number of V cycles that we're going to do, for example. We're going to assume that the R is chosen such that gamma to the R power is less than a half. Okay, strictly less than a half. That can always be accomplished if R is big enough and gamma is small enough. Let's say, for example, gamma is equal to, well, let's see, so 1 over the square root of 2, for example. If we take R equals 2, then this gamma to the R is 1/2. So it doesn't quite satisfy that. But if we take R equals 3, then it will satisfy that. We'll get a gamma to the R, which is less than a half strictly. Now suppose that UL hat is that function in VL, which connected through the basis BL is the same as the output vector from the full multigrid algorithm on that level L. Okay, so in other words, all we're doing is saying the vector output from the full multigrid algorithm gives rise to a finite element function. These are the coordinates of this vector or of this function. Coordinate vector through the basis gives a function, as always. So suppose that we have that. Then there exists a constant independent of L such that the solution that we want, this is the finite element solution, minus the solution that we're generating by running our full multigrid algorithm to level L, measured in the H1 semi-norm, which is the same as the H01 full norm. This is just the norm which has the gradient-only parts, is less than a constant times HL times the 2 norm, the 2 Sobolev norm, or sorry, the 2 Sobolev semi-norm of the true solution U, where UL is the finite element approximation of the problem on level L. So this is the standard way to write the finite element approximation. And U is the true solution for the problem in this infinite dimensional space H01. So remember, if f is an L2 function, then U, by a regularity theory, can be assumed to be, if the domain is sufficiently nice, can be assumed to be an H2 function. So that's essentially what we're assuming here. We're assuming that the domain is sufficiently nice so that if f is L2, then the true solution gets this regularity bump. This is what is called a regularity pickup or a regularity property, something like that, where U gets bumped up from this space to H2. So let's prove this. So usually we define something called the error at level L. So that would be EL is U minus UL. And this would be a function in H01. That's usually how the error is defined. Now we're going to define something called EL hat, and that's going to be the difference between the finite element approximation and the object that we produce via the full multigrid algorithm on level L. Remember, the output of the full multigrid algorithm is a vector, but we're going to convert that to a function via the finite element basis. Remember, we can always do that. If we have a vector that describes the coordinates of a finite element function, then we can immediately pick up the finite element function it's describing. This is what is called the algebraic error for computing the finite element approximation. The algebraic error. Okay, it's not the error the same, it's not the same as this error. It's the error, the algebraic error of applying our solver. Remember, solvers don't actually always give the exact solution. I guess if you have exact arithmetic and you're using the Gaussian elimination in exact arithmetic, that will complete to give you the true error, but you're never using exact error or exact precision whenever you're using a computer. You're always going to have some round off error. In any case, we're having something, we have something more than round off error because we're using this iterative process. We have something we're calling the algebraic error. Okay, now the algebraic error is clearly 0 on level 0. That's because we're going to assume that we use exact arithmetic to invert the stiffness matrix on level 0 and get the true solution. Now, we can measure this algebraic error, EL hat, in the H1 seminorm, which, let's square that. So that's just exactly equal to, by definition, A inner product, or bilinear form, of EL acting on itself. Okay, so this can be written as this vector norm in the vector norm AL. This is what we call the energy norm. And where EL is the set of coordinates for this difference vector here. Okay, so for this, or this difference function, EL hat vector, or bolded, is going to be my coordinates in the basis BL for that algebraic error. Okay, this is an easy thing to show. I'll leave that to you as an exercise to do it, to work it out. But I hope you see it's not too hard. So again, this is the vector coordinates of this finite element function in VL. By the way, this function is not a finite element function. Does everyone see that? This guy here is not a finite element function because this solution is in H01. It's in infinite dimensions. This guy is also in H01. It's actually in the subspace VL. But if I take the difference of those two, I end up back in the infinite dimensional space, not the finite dimensional space. Whereas this difference here is in VL, so we're good. We're good in the sense that we can come up with a coordinate vector for that difference. All right, so let's measure this guy. All right, so this in H1, we argued was this difference vector in the vector norm AL, the energy norm. This is less than or equal to gamma to the R UL minus the prolongation of the solution at the previous level. This is how the algorithm is defined. You prolongate up from the level L minus 1 to get the initial solution at level L. Okay, so keep that in mind. Now this, I argue, is just equal to gamma to the R. That stays the same. UL minus 1 hat in the H1 seminorm. This again is just a finite element function. But look at it. This guy here is the difference between a function in VL and a function in VL minus 1. So where does this live? So since VL minus 1 is a vector subspace of VL, if we have a function in here, we can add it to any function in here. And we get a function or a difference that results that lives in this space VL. So that's where this guy lives. And it's just an exercise to show that this norm here is equal to this norm without with exact equality. Okay, not too hard to show because this is the coordinate vector of this finite element function in the space VL. So that's just a fact. Now, let's look at this error here. This is the algebraic error between the solution at the finite element solution on level L and the thing that we generated via the full multigrid algorithm at level L minus 1. And let's use the triangle inequality. What we're going to do is add and subtract a couple of functions. The first thing we're going to add is the true solution to the PDE problem, u. And then we're going to subtract that guy. Then we're going to add the finite element solution at level L minus 1, and then we subtract that guy. And that gives us, if you do the triangle inequality, 3 things that we have to estimate. Now, let's think about this. This is the difference between the finite element solution and the true solution u. So this, measured in the H1 norm, is this just uses our regular finite element error approximation. So we get that. The same with this term here. This is just a finite element error approximation. Now, notice this lives in L minus 1, so that's going to give me HL minus 1, but I get a 2HL because HL minus 1 is just equal to 2HL. All right, so these are my 2 finite element approximations, but at different levels, and I get the same order of magnitude. Well, what about this guy? Well, look at what we're measuring here, EL hat, okay? EL hat, that was the difference of the true solution at level L and the solution at the full multigrid approximation at L. This is more or less the same, but at level L minus 1. All right, so that's the same, but at level L minus 1. All right, now, so what do we have then? What do we have? So that we're just going to multiply this through, okay? Well, this is just recognizing or rewriting that like that. Where did these other things come from? Let's see. So these are the error approximations. Let's see, and then this is just by definition. Okay, so I've only done the error approximations going here to here. So we're good so far. And now we're just going from this line to this line, we're just rearranging a couple of terms. We're going to combine these two. This, of course, is this looks the same, right? So this is 2 times a constant. This is 1 times a constant, but they're not necessarily the same constants. So when we add them together, we get a new constant, but it might not be equal to 3 times c. It's just some new constant, which we're going to call generically c. So c gamma r HL, that's just the combination of these 2 terms with this guy, this product. And then, of course, I've distributed this to this term here to get gamma r EL minus 1. Now, by the same reasoning, if we do the same analysis at the level below, we get a similar sort of thing. Okay, so this is kind of an inductive step. So if we do the same analysis, but at level L minus 1, we should get the same thing, right? These should be the same. The only difference is this is, instead of HL, this we're going to write as HL minus 1. We still have this same H2 Sobolev seminorm. We're going to get error, but at the next lower level, in this case, is going to be the level L minus 1. And this, again, is an algebraic error measured in the H1 seminorm. So now let's combine 19 and 20 together. So 19 is this guy here. 20 is this. Same reasoning to get both of those. And so what we're going to do is substitute this right into that term there. So if we do that, then we get this term that comes from here. And now we're going to apply this to that and that. So we get gamma to the 2r, okay, HL minus 1, and gamma 2r for this term because we have a gamma r here, so there we go. So I think you can see what's going to happen. Now we're going to apply the same sort of logic to approximate this guy and go all the way down to the basement.
Dr. Wise,
Yeah.
can you move your cursor away on the screen? Yep.
Okay.
And also one more question. So we are just applying induction argument, or can we directly use the discrete ground wall inequality?
Let's see. So we don't need to use Gronwall. I don't think we need to use Gronwall. I'm trying to think about how Gronwall would be applied.
Because
So
you essentially have like an equals to a constant times another constant times an minus one, right?
yeah.
So
So would it be applicable in this case? Um, I'd have to think about that.
okay,
In any case, we don't need to use such complicated technology. We're actually just going to use something simple like a geometric series.
okay, got it.
Okay, so something simpler works for our purpose here. You can see what's going to happen. What I'm doing is building up terms which look like this, and I can pull these factors out. Eventually, this term is going to get me down to e hat 0, which is going to be 0. So it's going to terminate, and I'll just get some sort of series. So here it is right here. Okay, so if I've got L levels, what do I get in the next step? I get 3R, then 4R, going all the way up to level LR. Okay. Each level, though, has a different value for H. Okay, so HL minus 1, HL minus 2. But of course, these are related to each other in a very standard way, right? So HL minus 1 is just 2HL, and this is going to be 4 times HL, and then 8 times HL, etc. So what we can do is effectively factor out CHL, let's see, over 2, I guess. Where am I getting the 2? Because I want to put a power of 2 here, an appropriate power of 2. So I want 2 gamma r there, 2 squared gamma 2r, 2 cubed gamma 3r, etc., up to 2 to the L gamma L to the R. And notice I pulled out this factor of, I think I'm missing a term here, right? So I think what I'm missing is this guy. Give me a thumbs up if you think that that's right. I
Yep.
think that's right. Missing term. All right. Because it can't disappear and then reappear, right? With equality, I don't think. I think we're okay now. Right now, so this is just a part of a geometric sequence. It could go on, right? Ad infinitum. Uh, for example, we could let this L go off to infinity. Gamma is, of course, something which is smaller than a half. So that when we write 2, when we compare 2 with gamma, we're going to get a number which is uh, less than, uh, less than 1. Right? So what we want is to produce, so first of all, we can add all the rest of the terms of this sequence going out to infinity. That's certainly going to give us something which is larger, which is why we get the increase here. And then when we put everything together, this is just going to be a full geometric series, and we can find out its sum, right? Now, let me see. Is that exactly what I did, or did I use the partial sum of the series? I can do either, I guess. Could do either. I guess that's what I did do. I used the fact that this is only finite. But in that case, why didn't I use equality there? Um,
I mean, if you use the sum to infinity formula, it should be a strict
right.
equality.
This shouldn't appear, right? Is that right? Oh, no, no, no. It's
No,
right.
no,
It's right.
that's correct. But I
It's right.
mean, yeah.
It's right. So I add all the terms going up to infinity. That gives me the increase. So I guess if I would do an extra step, it would be adding the terms. And then this is the exact sum of that geometric series. And of course, this works, right, if this whole factor here is less than 1, which is what I want, of course. And that's by assumption. I think I misspoke, but it's gamma r is less than a half strictly. So that means if I take the 2 and multiply it over, then that's strictly less than 1. So 2 gamma r is less than 1. 2 gamma r is less than 1. Okay, so I'm safe there, right? So that's just some fixed number. Now, why does that complete the proof? Well, because I have an h here, right? And I have my 2 Sobolev seminorm of the true solution here, and there's my h. Now, this is just some constant, right? Once I fix gamma and fix r, then this is completely fixed. This is just a constant. So that proves the theorem, the thing that I wanted, right? I wanted to show that the algebraic error is less than a constant times HL times the 2 Sobolev seminorm. All right, so that shows that the full approximation, or the full multigrid algorithm returns a solution which is pretty darn good, right? So it's saying that the difference between the finite element approximation and the thing which I'm returning for my full multigrid algorithm has the same relative error as the finite element solution does in the first place in the energy norm. In fact, the next remark addresses this. So remember, if we look at the difference between U and the finite element approximation, we proved that this is less than a constant times HL use 2 Sobolev seminorm, order 2 Sobolev seminorm. Right? We already showed that. That's a standard for basic finite element error estimate. So it combined two things. It combined Say's lemma and then approximation theory from interpolation error. So that's that. So now let's look at the difference between U and this thing we produce by our full multigrid algorithm. So that's, remember, U hat is not the same as that. Does everyone see that? U hat is the thing produced by the full multigrid algorithm. That's not necessarily equal to the true finite element solution. There's some algebraic error associated with that. Let's add 0 by adding UL and subtracting UL and use a triangle inequality. Well, this is the same as that, so we can replace that with that error. And this is the error that we just generated. And they both have the same order of magnitude. So when we add them together, we're going to get some new constant. And this is very common in numerical analysis. If you have a constant, both of which are independent of certain parameters, in this case, both independent of L, we're just going to add the two together to give a new constant, which we're going to relabel with the same name. It's an abuse of notation, but it makes sense because we don't want to keep labeling this C1, C2, C3, etc. It gets a little tiring. Now, this says that the difference between the error or the exact solution and the approximation that we generate via our full multigrid algorithm is just as good as the one that we would have produced by the finite element solution altogether. The way you can think about it is, roughly speaking, this is going to be 2 times larger than that. It's going to be roughly 2 times larger than that because it has that error in it plus another algebraic error. So figure it roughly to maybe 3 times larger. But it's still going to be the same asymptotic order. It's still going to be order HL as HL gets smaller and smaller. So the question is, why go any further? Once you have something like this, then you can just call it done because it's just as good as in terms of accuracy from an asymptotic point of view as the error of the finite element solution. So why not just stop there? Why go any further? Okay. So the answer is you don't have to go any further. You have the right asymptotic order of accuracy. You can stop. And again, this is about twice as large as the finite element error, maybe 3 times as large, maybe 4, but it's still the same asymptotic error, so we can stop there. Now, the next result is it shows that our finite element method is actually, this new finite element method that we're computing is actually cheap to calculate. That's because the cost of this full multigrid algorithm is optimal. That's what we want to prove next. So this is what it's called a work estimate. And if you're into building algorithms, work estimates are your bread and butter. We haven't done any work estimates yet in this course. This is our very first one and maybe even the last one, but this is all we really need because it's the thing which shows the optimal accuracy or the optimal order in terms of work that is provided to us by a full multigrid. So here's what we have to assume in order to get there. So let's suppose that we have a level dependent mesh, right? And a finite element space associated to that. Now, in one dimension, we showed, if the thing is uniform, we had an exact formula for this guy. In 2 dimensions, you can also get a formula for it. And basically the idea is, here's roughly the idea. So if we're in 1 dimension, then roughly speaking, if we use a uniform mesh, then NL goes like 2 to the L. So that's in 1D. So let's see if this holds. So this is level, so what did we have 1, 2, 3. This is level 3. How many elements do we have? We have 1, 2, 3, 4, right? So let's call it instead level 2, which is what we could do. So it has 4, L is equal to 2. If we go to 3, then we're going to get 8 elements, right? So the degrees of freedom are roughly going to be 8. Now, it's not exactly 8, it's actually 7, but let's not worry too much about that. Roughly speaking, the number of elements goes like 2 to the L, okay? Now in 2D, instead of having a mesh which looks like that, we have a mesh which looks like this, for example. And to refine this one, we cut it in a specific way. And you can show that the number of elements in this mesh goes like 2 to the 2L, 2 times L, okay? And the extra 2 comes because of the dimension, the increase in the dimension size. So if we're in 3 dimensions, you guessed it, this becomes a 3 there for 3 dimensions. So generally, we can replace this with the number of elements goes like 2 to the D times L. Now that's an estimate. That's because you don't exactly have that number of nodes. Remember, the number of nodes that are free are, you count them this way, number of interior nodes. And here there are only going to be 9. But asymptotically, they grow like this parameter, okay? The way we can show this is that, or the way we can state this more generally is to assume that the number of degrees of freedom is bounded below by a constant times 2 to the D times L and bounded above by a constant times 2 to the D times L, where C2 is bigger than C1. Okay, so this is really this is saying asymptotically that everything goes like 2 to the D times L. Kind of easy to show here and here for these simple mesh cases. But if you get a more complicated mesh, then this becomes a mesh assumption. It's a reasonable assumption at that. Okay. Here D is the dimension, of course. Now let's suppose that P, this is a technical assumption, P is less than 2 to the D power, 2 to the D power. So that means if we're in 1 dimension, then P should be less than 2. So this means that the amount of work that we're going to calculate is going to be for P equals 1. And P equals 1, that gives the V cycle. Otherwise, we can take P larger and these estimates that we're going to calculate hold. This is just some technical assumption, which I'll show you where we use this as we're going along. Now, the amount of work, total amount of work for computation for the full multigrid algorithm, okay, we're going to label that WS for level S of the full multigrid algorithm is bounded by a constant times n to the s, that is the number of degrees of freedom at level S, which is the same as saying, roughly speaking, WS equals big O and S. Where C is some constant, of course, C has to be a constant which is independent of these levels. I could write it differently. I could write it as, come on back. No. I could write it as this. Okay. Don't have to use S, we could use L. All right. Let's prove this. So this is kind of a complicated and technical proof. It's not impossible, but it is kind of complicated. So pay attention to the details here. Let's let little WL, so this is different than capital WL. Let's let this denote the work required for computing the output of the multigrid operator just at level L. Okay, just one application of not the full multigrid algorithm, just the standard multigrid operator for any of the levels. Now, what we're going to assume, and this turns out to be a very reasonable assumption, is that the work is dominated by smoothing, or at least the cost can be estimated by estimating the smoothing costs. That's the most expensive operation in the whole procedure. But think about what you actually have in multigrid. So in multigrid, we have 3 steps. We have the smoothing. We have coarse grid correction, which involves a restriction and a prolongation. And we have then again smoothing. So the only thing that we're not going to count in this operation is essentially the prolongation and the restriction. We're only going to count the smoothing and then the cost to apply the coarse grid correction. We're going to kind of count that as a whole. So this does neglect those costs of restriction and prolongation, but those costs are very minimal compared to the cost of smoothing. So it makes sense that they can be dropped. Or another way of thinking about it is just if it's 3m1 plus m2 to do smoothing times nl, then just tick this up to say 4. Let's make that constant instead of 3, make it 4, and that will account for prolongation and restriction. Okay, so and that gives really a big overestimate of actually the cost. So this cost here, say the cost of one application of multigrid, this takes care of smoothing, and then this is the coarse grid correction. Remember, coarse grid correction is applied p times, so we're gonna tabulate that cost as p times the cost of doing multigrid, but at the lower level. Remember, because multigrid is a recursive algorithm. C should be level independent. That makes sense because smoothing always has the same structure, which depends on the number of smoothing iterations times the total number of operations. Now, it might sound like smoothing should be more expensive since it involves matrices, but actually it's not. And that's because, as we'll show when we talk about, when we look at chapter 7 in more detail, smoothing is really in a local application, a local process. That's because it turns out that the matrices that are involved with the finite element method, namely the stiffness matrices, are what we call sparse matrices. So this is the cost of smoothing. This is independent of L. Now, similarly, at the lower level, at the next lower level, we have the same kind of cost structure, right? Asymptotically speaking, it's CM1, that's pre-smoothing, M2 post-smoothing, total number of degrees of freedom on that level, level L minus 1, and then the cost of doing the coarse grid correction at that level. Now, of course, at the lowest level, that's L equals little l 0. Whenever this becomes, this sum here, this difference becomes 0, then we can just estimate that cost as just being some fixed number. So we're going to combine these last two estimates together. And the way we're going to do that is use this estimate and then take this guy and push it into there. And when we do that, we of course multiply p times everything. So p times that term, and then we get a p squared multiplying this term here. Okay, so that is the cost of doing 2 levels. And of course, we can continue in this fashion. And what we pick up when we go all the way to the end is some structure like this: NL, P and L minus 1, then P squared NL minus 2, all the way down to PL and 0. And that's whenever we exhaust this number, going all the way down to its smallest possible value. So this is just carrying on those estimates all the way down to the lowest level. And now we're going to use the property that we said, this little technical property, that P is less than 2 to the D. So when I use that, then I can replace each one of these P's by these numbers here. And again, what you see is what is happening is I have a geometric series. So this is like P to the 2D to the 0 power, to the first power, second power, going all the way up to power L. And I pull out all the other common factors that are in these terms. Okay, so 2, in particular, 2 to the DL. That I have used one other estimate, and that is that this guy here, NL, is bounded above by this constant here. Okay, so that's how I know that my NL is going to some, it's basically NL is going like 2 to the D times L. That's where I'm using that. Okay, so those are the two assumptions that I'm making about the structure of my problem. Now, once again, this is just the part of a geometric series, right? It's a finite part. So if I increase this all the way out to L equals infinity, I get something bigger. But of course, that's the tail of a geometric series, which is getting smaller and smaller. And I can therefore say that this whole thing is less than this number. Okay, so there's the sum that is involved in my geometric series, this guy here, I guess. All right, and then one other substitution. Now I'm going to come back and replace this with something which is a function of NL, and I'm going to use the fact that, let's see, so if I want to go this way, if I have 2D times L, so I knew that that was less than C1 NL, and so I'm going to divide both sides by C1. And that's how I can replace this guy with NL. Okay, and so then everything else is just a constant which is independent of L. So I can call that my C. Now, the last thing that I have, this is the cost of doing a multigrid application at each level. Okay, so that's the cost at each possible level. But now what I'm going to do is I have one other step in the process, and that is the prolongation step. But the cost of prolongation is, again, very cheap. So it doesn't really factor in. Another way you can look at it is the cost of prolongation is just make this constant maybe 1 more. Okay, so it's very cheap, but I can neglect it altogether, actually. Now, if we neglect the cost of the prolongation step, then the total work in getting to WS, that would be the work for S minus 1 plus applying the multigrid operator R times, because that's how it works, right? Of course, I've neglected the cost of the prolongation and pushing the vector up, but otherwise, the cost of the full multigrid algorithm is the cost of the full multigrid algorithm at the level below, plus the cost of our applications of the standard multigrid operator, which cost we tabulated as small ws. Now we know that the cost of ws is related to cost or just the sum bounded below or bounded above by some constant times ns, and so that's where we replace, that's how we can replace this with that. And likewise at level s minus 1, this just keeps working backwards, right? So now we can put this cost into there, and you can see we can run this all the way back, right? So there's two applications of that cost. And if we keep going back, we get something which looks like this. Okay. The costs at level S for one multigrid operator and times R times the cost at the next level all the way down to the 0th level. So we have this common factor of R which appears in each term, a constant that appears in each term as well. We can take the maximum of those constants, but those constants are roughly the same anyway, so we don't have to worry about that. Now, the next step, we're going to replace these NS's by using this estimate. NS is less than CS times 2 to the L. No, let's see. This is going to be S times D. Okay. So we replace each one of these guys with terms which look like that. The thing that's changing at each level is this is becoming smaller and smaller, right? That level number becomes smaller all the way to 0. So we have something which looks like that. Okay, now we can take out the largest of these guys, which is this guy, pull out the largest, and then that gives us this sum. Again, the same thing appears, geometric series, right? Well, at least the finite portion of a geometric series. But if we run this all the way up to infinity, that gives us something which converges, and it converges like this. Now we do a couple of manipulations on this. We're going to do what we did before, convert this back to NS, same sort of way. The rest of this stuff does not depend on S. So we get an NS and some constant which doesn't depend on S. And that whole thing we're just going to call the constant C. So we're done. That's the proof. We've shown that the full multigrid algorithm has a cost which is less than a constant times NS. And this is remarkable because even if R is like 3 or 4, the fact that R is finite means that that's just built into this constant. And it goes, you can see, if we increase R, then this constant here goes linearly like R. So if we take R to be 4, then it just grows like 4 times the total number of elements in the total number of unknowns in the vector that we're looking for, NS. So that proves the result that we're looking for. I'm going to stop there. You can turn your cameras on, and I can take some questions that you guys might have about this. So talking about full multigrid algorithm.
I have a question.
Yeah.
Can you go back to the algebraic error, like concerning the algebraic error?
Yeah.
That theorem. Yeah, 2 page earlier.
Okay.
Yeah. Okay. So so one part of the theorem that is important is that we know that the C we get at the end should be independent from capital L, right?
Correct.
So my question is, I'm not that convinced about that because
Okay.
we know that for any finite element estimation, we have a different C, right? And now when we are writing out the proof, we're kind of doing like so the C is kind of getting like bigger and bigger. We kind of add it, right?
So the good news is C does not depend on L, and it doesn't change. It's only a constant which depends. You should think about it like this. It's only a constant which depends on the shape of the domain. So if it's a square, it's one type of constant. Or
Okay.
or if it's a triangle, it's one type of constant which does not change. And the only thing that encapsulates or that tabulates the dependence on L is this constant or this parameter here. Okay. So the way the finite element error estimate is structured, let me see if I wrote it somewhere else. I guess I didn't. The way that it's structured is, let's go think about the standard finite element approximation. H01, that's less than a constant. HL, U, H2. Okay. So this breaks the error into 3 parts. So this one is a structure factor, which is kind of quantifies the domain. This is the resolution of the mesh within the domain. And then this is the exact type of function that you apply on the domain. But the domain only, well, the C constant only depends on the structure of the domain. So
I see.
is it a square? Is it a triangle? So it kind of quantifies the shape.
Okay, but still, look at equation 19.
Okay.
The C that we have here is kind of like 3C, where C is depending on the shape, right?
Yeah. So it
But
would be like, so this really would be like 2 times the shape factor and 1 times the shape factor. Yeah. But luckily, so yeah, you could think about this as 3 times that could be combined into that. So it's 3 times that. Yeah, but it never, so it doesn't grow, it's not going to ever grow because this is going to be the same factor at each level. Okay, so this is going to be 3 times that structure factor, whatever it is appearing on each level. So again, it's not like it's 6 here, it's still 3. Okay, so then when I
okay.
add these two guys together here, let's see. Well, let's see. So okay. Oh yeah, see this one here. We're not going to add these two guys together. We're going to bring this constant out together using distributive property. So the good thing is they're not going to get added together. Okay.
I see.
This
Oh,
guy is going to get pulled out by the, so see all these constants are roughly the same. So I'm going to pull them out using distributive property, not add them together.
I see. I see. I'm
That
thinking about adding them. That's why I'm just thinking why they're independent from L.
That's an excellent observation. So the reason why you don't get burned is because you don't have to add them all together. You get to pull that structure constant out using distributive property. The same with this guy. You get to pull that thing out because of distributive property. So if you had to add them all together, then you would get burned.
Got it. Got it.
You survive here because all of the level variation is obtained via a geometric series. That's the way you have to do it every time in order to get constant, which doesn't grow linearly or
I
worse.
see.
All right, so we just showed or talked about the full multigrid algorithm, showed that the result of that algorithm could give us an approximation, which is just as good as the original finite element approximation we're after. So, and then we showed that using some number or some application of the full multigrid algorithm is enough to get us an approximation, which is in some sense good enough. And then we showed that the cost of this full multigrid algorithm is optimal. Now I want to show you the results of some computational experiments with the caveat that I'm actually going to show you the application of just a standard multigrid algorithm, not the full multigrid algorithm where we go, you remember the diagram of full multigrid, you go from the bottom to the top. We're just going to do a standard multigrid algorithm where we just go from the top, some sort of standard V cycle or W cycle. It turns out that that's cost effective enough for us. So, all right. So some computational experiments. So I'm going to cheat because I'm cheating because we did all this work in multiple space dimensions, 2 and 3 possibly, but I'm going to show some computational results in 1 dimension. So in that sense, cheating. The solution is going to be something which is only 1 dimensional, of course. It's going to have 0 boundary condition. The exponential of some sign function. And so I'll show you what this looks like momentarily, but just keep in mind it's 1 dimensional. So the stiffness matrix is the standard stiffness matrix computed from 1D finite element. The reason why I'm using 1D here is because I can use uniform mesh, and then I can the stiffness matrices are very easy to compute. I don't have to use any complicated data structures. Later on in the course, and this may be into the next semester before we get to it, we'll show you some computational experiments using a finite element software package called IFEM, IFEM, by my good friend Long Chen. And this one will be in multiple space dimensions and using some interesting meshes. But before we get to that, we're just going to rely on these computational results in 2D, or sorry, 1D. So what we're going to do is we're going to start off by assuming that we have this as our true algebraic solution. So there's our algebraic solution. And what we're going to do is once you have an algebraic solution and you have the stiffness matrix, what we're going to do is just multiply the stiffness matrix times the components of that algebraic solution. And that gives us the loading vector. So rather than compute this from some L2 function f, which is what we normally do, we're going to do something called manufacturing the true solution. Okay? Or we're going to manufacture the forcing vector by constructing the true solution from a known vector. So this is known. We now know what the true solution is because we're going to manufacture the right-hand side so that that is exactly our true solution. Okay, so but let me emphasize that what you do is you get UL first. Okay, get that first, and then you compute F by taking the inverse. Let's see, I did that wrong.
You
So think
just
about it
left
like
multiply with AL.
yeah, you get this first, and then we're going to multiply by the inverse. This is or not. No, not by the inverse. Just multiply by a on the left, and then we're going to set this guy equal to that. No inverse required. I don't know why I was saying that. So just multiply by the stiffness matrix, and then we get the forcing vector that we want that is associated to this. But the order here is important because when we're testing our solver, we want to have a true solution to see how good we are to baseline. So get this first, multiply by the stiffness matrix, and then we have our forcing vector. Then we're going to forget that we know this guy, and we're going to throw some random initial vector at the algorithm and try to then to compute that. And then once we compute an approximation, we'll call that something like UK. And then we can take the difference of that. That'll give us the error at level L. And then we can, of course, compute the norm in some norm of that guy. And then see how fast does this guy go to 0 as k goes to infinity. Okay, so that's what we're going to do. All right, which is explained here in the lecture notes in the book in some detail. So we manufacture our right-hand side because we manufactured our true solution. And then we're going to choose an initial guess by some pseudo-random number selection. We oftentimes what people do is just set this vector equal to 0. Okay, but we throw some random numbers at it instead. So on the next slide, I'm going to show you the results of doing our multigrid V-cycle algorithm with p equals 1. Okay, so V cycle, not a W cycle. W cycle would be P equals 2. And using the smoothing parameter 2/3, and using a balanced or symmetrized smoother where we do 3 post-smoothing and 3 pre-smoothing steps, M1, M3, M2 equals 3. We're going to use to start with NL equals 255. So this is 1 less than a power of 2. So 2 to the power 7 minus 1, I believe. Capital L is equal to 7. Okay, so here's the result of our approximation. I'll show you what the true solution looks like and how this works momentarily. So we start off with a pretty this is our number of iterations, k, along the bottom. This is the error, and this is error getting smaller, but it's measured in a semi-log scale. So it's measured with logarithms on this axis and k on this axis. All right. So what we see is that we get a nice steady reduction in our error. This is the true error that we're computing here. Now, that's in the blue. In the red, what we're showing is the difference between two successive approximations on level capital L. And what this shows is that using these red numbers as an error estimate is a pretty good over error estimate, and it decreases at the same rate. So this is when you know the true error, which we don't know in practice. What we really know is maybe something like this, but we can use this as a stopping tolerance, okay? Roughly speaking, this is like 5 times bigger than that, that's reasonable. We don't know what the true error is, so let's use an error estimator, which acts similarly. So for these input parameters, M1 equals 3, M2 equals 3, P equals 1, and the smoothing omega is 2/3, then we get a reduction factor, error reduction rate of 6 times 10 to the minus 2. That means that the error measured in the L2 norm is reduced by a factor of roughly, well, almost 100, right? Every time I do an iteration. It reduces it by the factor of 6 times 10 to the minus 2 every time I do an iteration. That's a very good contraction number. Now I can play around with the different multi-grid parameters to see if I can do a bit better. So for example, in this table, I'm doing a similar calculation here, but where instead of using omega equals 2/3, which would be somewhere in here, I'm going to use a range of omegas. Okay, so omega from 0.5 up to 0.8. And what I see is actually, if I do the same number of smoothing iterations each time, so 3 pre-smoothing, 3 post-smoothing, roughly I get the smallest contraction factor at this stage right here, 5.3 times 10 to the minus 2, which corresponds to doing omega equals 0.75. Now, if you recall, using omega equals 0.5, that corresponded to the best, well, this corresponded to the omega that is suggested by using Richardson's smoother. And 0.666, or in other words, 2/3 is that's the smoothing parameter that we derived in chapter 3 as being kind of the best. Looks like, according to our experiments, that something around omega equals 0.75 gets the smallest reduction. And then we can do some other things. For example, we can play around with different values of P. So here, play around with 2 different values of P. So it looks like you get a better contraction factor when you use 2, P equals 2. So this is the classic W cycle, and you can compare that one to this one. So you go from 8 times 10 to the minus 2 to 5 times 10 to the minus 2. But still, that's not even as good as this guy. So in fact, doing something really complicated like a W cycle doesn't actually necessarily yield or do something better than what you can do with the V cycle algorithm. And doing more applications of a W cycle, that means going from P equals 2 to 3, doesn't always net you any faster convergence. Here, I'm only going from 5.44 times 10 to the minus 2 to 5.42 times 10 to the minus 2. So it doesn't net me very much more. All right, so I'm going to stop there. These are the results of some very basic computational experiments. And next time, I'm going to actually break out the code. I had that ready to go this time, but I got a little bit too chatty, I guess. So I'll show you a code demo if you're interested in running code. The code is written in MATLAB, and it's, I think, fairly accessible and easy to use. So that's what we'll talk about next time. And then after I do this code demonstration, we're going to go into chapter 8. So we're going to skip chapter 7 for now because it's not finished writing. That one should be finished writing in maybe a couple of weeks. We'll do chapter 8 and maybe chapter 9, and then we'll come back to chapter 7. Okay, so that's a roadmap for the future. Yeah, I'll stop there and take any questions you guys have.